Howdy, everyone. Happy Wednesday. Happy end of March. We had our exam on Monday. I don't know how the grading is doing, but sometime this week it'll be done. It seemed to go well. We didn't have anyone miss the exam that we expected to take it, and I don't think there were many glitches in people trying to upload the exam. I think all of you probably know we will not have class Friday. It's day off. It's Good Friday for many people. So there's another day missing in our schedule. So today and next Monday, we will try to finish off everything with electronic spectroscopy. And then the rest of the semester will be statistical mechanics, which I think is important for chemical engineers. I put this slide on, we talked about this topic before. This shows us why plants like red or blue light. They don't like green light, they reflect it. So we have the chlorophyll molecule. Here's a picture of it. Its molecular orbitals are very complicated, but the electronic transitions take place there. Okay, there I have a personal chat that I was reading, sorry. Anyway, this is a molecule found in most plants, and I've often liked to say that we wouldn't be here on planet Earth if it weren't for electronic transitions, and here's an example of how this works. So plants absorb light at these frequencies in the blue and red regions. Plants can grow, and then the rest of us can thrive on planet Earth. Just to remind you, I think this is the slide I want. When we talk about electronic spectroscopy, basically we're talking about electrons jumping from filled molecular orbitals into empty molecular orbitals. So this was a diagram for NO2 that I showed you some time back. But what I want you to see, it starts getting pretty complicated. So in principle, any electron here in one of these lower orbitals can have a transition up to a higher orbital. Now, some of those transitions are more allowed than others. They'll be more intense, more photons can undergo it. But in principle, you can go from any lower orbital into a higher orbital. So this is what we're dealing with when we talk about electronic spectroscopy. Any individual transition gives us one new electronic state. And if you look at this diagram here, we have 3, 4, 5, 6, 7, 8, 9 orbitals that have electrons in them, 3 empty ones. So that's 27 possible electronic transitions that this molecule can have. So the whole field gets incredibly complicated when you start looking at it. Okay, so this is, I think, where we stopped last time. I drew a crude diagram for the molecular orbitals that you would have for a ketone or an aldehyde. So I pointed out we have a sigma molecular orbital, a pi, a couple of non-bonded orbitals. So we're looking at this group right here. And there would be empty orbitals, pi star and sigma star, the antibonding orbitals. So any of these transitions can take place. There are fewer on this diagram than I showed you for NO2, but there's still quite a few. And I think where we stopped last time, we got into discussing the fact that when a transition takes place, the electron spin should not change. So notice this is our ground state configuration. If we have a pi to pi star transition, we will take one pi electron and put it into this pi star orbital. This is what we'll have. Notice that this electron and the pi star electron are in opposite directions when we look at it. What I pointed out last time, however, was even though this is the only transition that's directly allowed, this other state exists. And this is the one where both of the electrons wind up in the same direction. So this is spin up and this one is spin up. We don't have time to get into it, but there are three quantum mechanical ways to represent this state, and it's called a triplet. And what we're also going to see is when we have transitions to singlet states, we can get the phenomenon of fluorescence. So we have fluorescent lights, but a lot of molecules also fluoresce. And then from triplets, we're going to get a phenomenon called phosphorescence. Things that glow in the dark generally come from triplet states. So they do get formed, and we'll see later today, hopefully, how these processes work. Okay, so this is the selection rules for spin. Singlet to triplet is not allowed. That basically says you cannot have an electron change spin. So directly, we would not see that transition. For the other transitions, there are symmetry rules that we won't get into. But for the diagram I showed you, the pi to pi star or sigma to sigma star, they're loud and strong. In general, the strong transitions are if you go from similar type orbitals to their anti-bonding complements, so pi to pi star or sigma to sigma star. So all of these other ones technically come out to be forbidden, but because electronic spectroscopy can be so strong and small perturbations like asymmetric vibrations can make some of these transitions become allowed. Some of these transitions you can see weakly, but the main transitions you'd see for a ketone or aldehyde would be these right here. If you think back to a ketone like acetone that you might have looked at in organic chemistry, most of them are colorless. So these transitions like pi to pi star occur in the ultraviolet region and you don't see them. So anyway, here's a summary. A sigma to sigma star transition would be in what's called a vacuum ultraviolet, really, really at high energies where even oxygen and nitrogen absorb, whereas the pi to pi star is around 50,000 Way numbers. These others, like N to pi sigma stars, if they can be seen and they're weak, then they would be maybe around 40,000 Way numbers, but still in the ultraviolet. An important point of this discussion is once we have a transition take place, we have a new configuration for the molecule, and the molecule behaves totally differently. So our ground state for our hypothetical ketone here was sigma squared pi squared N4. This is where we had our 8 electrons, 4 non-bonded electrons, 2 pi bonding, 2 sigma. If we have a pi to pi star transition, then this is our new configuration. 1 pi electron left, but we've added a pi star. And you can go ahead and then you can calculate bond order. This one had bond order of 2 with the 4 net bonding electrons. This one would have bond order of 1. So you'd have 3 bonding electrons minus 1 anti-bonding, take half of that. you have a bond order of 1. But the important point is when we look at the excited state, we don't only look at the energy change from going from a lower orbital to a higher one. Other things happen. For example, we've unpaired the 2 electrons that were in the pi orbital. So they had more repulsion when they were in the same orbital. So there's a larger energy change, or I should say a different energy change than just looking at the energy difference between the molecular orbitals that take place. Okay, so that's one thing to keep in mind. When we start doing electronic spectroscopy, we rely again on the Bohr-Oppenheimer approximation. We say electronic, vibrational, and rotational levels are separable. And we can, in general, add just the energies of each type together. And I will show you what I mean by that on the next page. And the wave functions wind up being the products of each of these. So we've already talked about wave functions for vibrations from the harmonic oscillator model, for rotations, and now we can have electronic wave functions. When we talked about molecular structure, then we looked at some trial functions that we could use, and so we have different electronic functions also. Okay, so in this picture, the book I took it from, and I try to show you what the big picture is. But let me emphasize again, this is a very extreme simplification of what there is. So we're basically showing a molecule, like a diatomic molecule, 2-atom molecule, and only one electronic transition. Again, think back to the NO2 picture for the molecular orbitals. I showed you 27 possible electronic transitions. This only shows one. So down here, we have the electronic ground state with our normal configuration of electrons in the lowest possible molecular orbitals. After a transition, some electron goes up, presumably to an anti-bonding orbital. And so this is at some higher energy. If we're in that carbonyl group and we have a pi to pi star transition, we're about 50,000 wave numbers up. So way, way high. Remember, infrared bands are around 1,000 or 2,000 wave numbers. So this is 50 times higher in energy. Going back down here, these are the different vibrational levels that we would have for a single vibration as in a diatomic molecule. So last time we were talking about vibrations, we talked about vibrational rotational spectra occurring together, and we looked at the first excited vibrational state and the lowest state. Each of these has rotational levels in them. So what's shown here, these are the pure rotational transitions that we talked about. I showed you the HCl spectrum, and we can calculate the bond distance from that. Then we looked at transitions from this set of rotational levels up to the first vibrational level. When we now look at electronic transitions, vibrational energies can change also. So on the right here, we're trying to depict, this is a potential energy curve that you'd have for a bond stretching, like in a diatomic. Here are a bunch of vibrational levels, and you can have transitions changing vibrational energies in the excited states. I won't have much time to tell you about it, but I stuck some spectra in that were taken in my own lab, showing how we can resolve and figure out what the vibrational levels are in an electronic excited state. That helps us understand what happens to the molecule when it gets to the excited state. I personally like to think a molecule, once it's excited electronically, as a totally different entity. In our ketone, if we have a pi to pi star transition, if the bond order goes from 2 to 1, the bond gets weaker, so the bond gets longer. When the bond length changes and the force constant gets weaker, vibrational frequencies go down, rotational constants change. So it's a totally different entity, really, that you're looking at. Okay, so there are a lot of features to this. One could spend a whole semester just trying to talk about the details of electronic transitions, but I'm trying to just give you the gist of it. When we look at transitions, a very important aspect is the Frank-Condon principle. And this is based on the following. We've already seen from Born and Oppenheimer that electronic motions are much faster than nuclear motions. So by the time an electron zooms around and by the time it can undergo a transition to an excited state, the molecule does not have time to vibrate or move. So I've been telling you molecular vibrations take about 10 to the minus, or there's about 10 to the 13th or 10 to the 14th per second. An electronic transition takes about 10 to 100 times less time than a molecular vibration. So when an electron goes to an upper state, the molecule doesn't have time to vibrate, doesn't have time to change its bond distance. Okay, so that's statement two. Electronic transition occurs before the nuclei have a chance to move significantly during the vibration. Thirdly, and I showed you this as an example, most electronic excited states have longer internuclear separations since antibonding character usually increases. So here again, this is now actually ethylene. It doesn't have the non-bonded electrons like the ketone does. But if we have a pi to pi star transition, you'll see that we go from a bond order of 2 down to bond order of 1. And this is a good chance for me to tell you how electronic transitions lead to photochemistry. You learned in organic chemistry, you can't rotate about a double bond. It takes something like 50 kilocalories per mole. But you can rotate about a single bond like in ethane, and that only takes about 3 kilocalories per mole. So if you start with, say, a substituted ethylene, maybe dichlorotrans ethylene, if you undergo the transition, that molecule can easily photoisomerize to the cis because it's easy to twirl about that single bond. Again, we just have limited time to talk about it, but I hope you appreciate how this can lead to a lot of interest in chemistry. A lot of chemical engineers wind up dealing with photochemical systems also, or maybe someone else has done the photochemistry and you wind up analyzing what's happened. But this is how photochemistry works. That's why the chlorophyll excited state business works. Some bonds get weaker. You might have twirling around bonds to have cis's go to trans and so on. Okay, so this picture now that I'm going to show on this page is meant to exemplify another aspect of the Frank-Condon principle. Most molecules we want to talk about are not diatomic, but it's easiest to talk about potential energy curves for diatomic molecules. But this is the kind of potential energy curve we saw for vibration of a diatomic molecule, or you can think of this as the curve for just stretching a bond in a larger molecule. So here's our electronic ground state. We have a bunch of vibrational levels. Here now is our electronic excited state. And notice that the curve has shifted towards the right. We assume the bond has gotten weaker because we're creating more antibonding character, and consequently the bond is getting longer. The Frank-Condon principle requires what we call vertical transition. So the abscissa here is the bond distance. So when the electronic excitation takes place, capital R, the bond distance, cannot change. The molecule does not have time to vibrate. So down here we see where the probability for this vibration is. So here's our chi-squared curve. And in order to get the transition to take place, it has to be able to go to a level, a vibrational level, that has probability at the same R value. Mathematically, it looks like this. We're back to the transition moment integral. When we multiply this whole business together, it's called the Frank-Condon factor. And we can only get a transition if psi sub I, the wave function for the initial state, and psi sub f for the final state, if they are both non-zero at the same place. So I'll try to show that here. If we try to go from an initial state, and here's the probability down here, and if our excited state has the probability to the right, the product of these two is always going to be zero or very close to zero, and so you would not have a transition. So the only way you can get transitions is if you go to a high enough vibrational state that these two wave functions can overlap. So both psi sub I for the initial state and that for the final state have to have non-zero probability at the same time. Okay, so as I said, this is called the Frank-Condon factor. Okay, I'm hitting you with this stuff really fast. We have some time to review it later, but also make sure you read the book to get more details on exactly what's going on with these systems. Okay, the next topic is what happens to an electronic excited state once you form it. So we've taken an electron from a lower bonding molecular orbital, shot it up by shining light on it, presumably, so it goes into a anti-bonding orbital. So once it's up there, that excited state is going to have a lifetime. It's not chapter 16 anymore, but you can read about that. And you'll remember we talked about the fact that the lifetimes get shorter and shorter as you go to higher energy. So electronic excited states have very short lifetimes, maybe only 10 to the minus 14 seconds or something of that type. So really very short lifetime. And that means that that molecule can have spontaneous emission and immediately fall back down to where it came from. And you can also have induced emission. When we talk about spontaneous emission, this fluorescence falls into that category, and I'll be telling you a little bit more about that. But so there are two kinds of things that can happen. Induced emission is what we're going to apply when we want to design a laser and have a coherent beam coming out with good intensity. So I'll be able to tell you about that too. Anyway, the three things that can happen. The first one is the most boring. This is called thermal degradation or non-radiative decay. This means you don't get any light out. It basically means you convert the energy from that upper state into heat. So maybe the molecule is up there something like 50,000 wave numbers. That's something like 150 kilocalories per mole. And it collides with another molecule, or it collides with a wall of the chamber, and it just transfers that as heat to the chamber. And so whatever it collides with, it can turn it into vibrational, rotational, or translational energy. Heat, you'll remember, is just infrared radiation that we have. The second thing that can happen, and to me this is maybe the most exciting thing, is photochemistry. And as I said, we've done a lot of experiments in my own lab just to see how molecules change in excited state and why they behave then the way that they do. And photochemistry, as we saw for plants, is just very, very important, or we just would not have any botany to talk about. The third topic, which I think is pretty neat also, is radiative decay then, and this is going to be fluorescence, which we think of as pretty much as immediate, or we can have phosphorescence as being slower. So I'm going to skip a page and come back to this one, but I have a prettier picture here. So here is our electronic ground state. Here's our electronic excited state. Typically, the way they're labeled, the ground state is S0. S means singlet, and that means the electrons are paired. And so up here, this is still where the electrons still have opposite spins, but we put a subscript on there because it's a first excited electronic state. And this is the most common transition that you will have. There will also be S2, S3, maybe even S48 and S49, lots and lots of possible electronic states. So in a typical fluorescence situation, you can excite the excited state either by absorption, by having light go into the excited state, maybe pick a particular vibrational level, or what is done for atomic systems, the fluorescent lights that you have in a room, they're probably based on mercury, atomic spectra of mercury. They are excited by just being zapped electronically, by hitting them with a high voltage, and the electrons shoot up to higher atomic orbitals, and then they emit from there, and that's how we get fluorescence. This diagram here is actually meant for what you would have maybe if you had a molecule in solution. And if you have a molecule in solution, very quickly molecules collide with each other and you get a little bit of non-radiative transitions. And so you just drop off and give off extra vibrational energy to wind up at the lowest electronic state. And then the fluorescence occurs, and this is isotropic, meaning equally in all directions. The fluorescence occurs by landing on some lower vibrational level that you have in the ground state. If we do vapors, as we do in my lab, then you can directly have a transition, say, from the B equal 3 vibrational level to one of these vibrational levels down there. So this is fluorescence. And I think this is relatively easy to understand, especially if you skip the part about the non-radiative transition. This pretty much occurs immediately. In liquids, the lifetime or the time that it takes for something to fluoresce is perhaps 1 to 10 nanoseconds, or 1 times 10 to the minus 9th seconds or so on. In gases, it can be quite a lot faster. The other picture on this page is more complicated. And I have a chat question. Let's see if that's relevant. There's a question of, are the transitions always 0 to 3? No, the electronic transition selection rule is delta V can be anything. So you can go from vibrational state 0 to 7 or 0 to 1. It all depends on that Frank Condon factor. What is the overlap of those wave functions that you have? But in terms of what quantum numbers change, it's independent of that. Okay, in this diagram, the electronic states are written 1A instead of 1S, and then 1A prime, I guess, for the excited state instead of S1, but it's the same kind of meaning. So this is fluorescence. Again, you excite a level, and you can come straight right back down at the same frequency that you put in if you're working the vapor phase. Remember that a normal absorption transition does not allow the spin of the electron to change. But I told you that the state where the spin has changed can also exist. So let's go back to where I had that. Okay, so here we can also have a triplet state. This state exists. And what I'm going to show you on that diagram, we have what's called inter-system crossing going from a singlet state to a triplet state. So what would make this happen? Well, what can make it happen is if the molecule with this configuration slams into the wall of the chamber or slams into another molecule, and spins are kind of sensitive to bumps, and so it can just flip the spin and you wind up in this state. And when you're in this state, you can't easily have a transition back to the ground state because the spin is not supposed to change. If this electron tries to come back here, they would both have spins in the same direction, and that is forbidden very strongly. So back to our diagram. This is then the intersystem crossing. So where this E indicates this is some kind of collision takes place, and it causes the spin to change, and we wind up in a triplet state. So the 3 here indicates it's a triplet state. There are actually 3 functions here. And now we're left in a pickle, you might say. The molecule is up in this state, and it knows it's not supposed to go back down to the ground state because it would be a triplet to singlet transition, requiring the spin to change again. So this turns out to be a very, very slow process. Again, molecules in their triplet states, maybe they have to collide with another molecule to make this transition take place. But you can get a trickle of these transitions taking place. Fluorescence, for fluorescence, essentially, all of the molecules can come back down to the ground state very quickly. For phosphorescence, I like to think of this kind of like a bucket of water with a tiny pinhole leak, and a few drops of water are coming out. So think of the bucket as being full of a lot of photons, and only an occasional photon can escape back to the ground state. It has to violate that spin rule, and to do it, it has to, again, have some kind of collision or have some other kind of process take place. So phosphorescence is what happens when you see things glow in the dark. I have a flashlight that has some kind of polymer rim around where the lens is. If I take it outside, it starts glowing, the rim starts glowing. And that's because when the flashlight is indoors, a lot of the dye molecules that are in that polymer ring wind up getting kicked into this triplet state over a period of time. And then when you go outside, they start trickling back out, and you don't see a very bright phosphorescence because there's only a few coming out, but it can last quite a while. So phosphorescence for a system can last several minutes, whereas fluorescence is on the order of nanoseconds or so. Okay, so that's kind of the summary of what happens from excited states. It's sort of thermal degradation, nothing. Then you can have photochemistry, which is exciting, or you can have fluorescence or phosphorescence. Okay, I'll go over these notes pretty quickly. These are my crude notes. It's no longer figure 1102 either. Basically, the first step is you have absorption. You go into vibrational states. And then if you're in solution, then you can have this radiationless decay. And fluorescence can come and land on many, many different levels. And you can see the fluorescence always has to be less energetic or lower in frequency than the amount of energy that you're putting in. So here's again a summary. In gases where a few collisions occur, the radiationless decay may be minimized, and fluorescence can occur from several vibrational states. Vibrational states always occur at lower frequencies. And here's our picture of phosphorescence. You have to have an intersystem crossing because it requires flipping of spin. And then you get slow emission because this is supposed to be a forbidden process. Let me jump a couple pages further. And this is from an old edition of Atkins, but this maybe gives you a better idea of fluorescence and phosphorescence again. So the energy levels for the excited states here for the singlet and triplet are those for naphthalene. And so one of the pi orbital electrons is excited to a pi star, and we create an S1 state. And you can see it says this is 315 nanometers. So this is something like 30,000. Well, in fact, you can see the scale here. It's maybe 30,500 wave numbers above the ground state. Slightly into the ultraviolet. Maybe a dog could see a color for naphthalene, but the human eye can't. All these horizontal lines are supposed to be vibrational levels, and it's actually a misrepresentation because it makes it look like they're all equally spaced. Naphthalene, I'm not going to count up all the atoms, but it's probably got somewhere between 40 or 50 different vibrations. Each of those vibrations has excited states. So there are just jillions and jillions of vibrational levels for each of these systems. Okay, so ISC stands for inter-system crossing, and this is how we get our triplet states. So these molecules collided and we get here. And notice now this number is something like 25,000 wave numbers, or maybe 27,000 wave numbers, I guess, or maybe 22, whatever. Anyway, the phosphorescence for naphthalene actually occurs in the visible region. So you could see a naphthalene molecule glow in the dark if you excite it for a while. I've never tried it, but if you have some mothballs at home, which is naphthalene, maybe put it under a bright light for a while, run outside in the dark and see if you see a color glowing. If anybody's silly enough to do that, report back to me and tell me if it works, but it's supposed to work. It won't work if the phosphorescence is too fast. It has to last at least some seconds, but if it's over in a millisecond or something like that, then you wouldn't see it much. This diagram also shows that once you're in the triplet state, you could have further collisions and just wind up in the electronic ground state in some very much higher vibrational level. And so this is inter-system crossing again, or what's shown up here when you have two matching quantum states. This is called internal conversion in going from the triplet to a singlet. So life can get a lot of fun and pretty interesting, and you get involved with all of this if you get into photochemistry. Triplet states, by the way, are very good for photochemistry because the singlet state doesn't last very long. So even if you've excited a molecule like ethylene into its singlet state, if it only lasts for 10 to the minus 9 seconds, it doesn't have much time to react with anything. But if it can get kicked over to a triplet state, which maybe hangs around for a few seconds, that molecule can collide with something else and have photochemistry taking place. Okay, here I had some just added comments. I think all of you are familiar that we have fluorescent lights. There you have mercury or neon lights. You use voltage to excite the atomic excited states. Phosphorescence can occur in organic dyes. It also occurs in elements like radium, which of course is radioactive. The next couple of pages, I'm just going to zoom over very quickly. Again, we're rather short of time. I hadn't realized we wouldn't have class on Friday, so that takes another class day out of our schedule. Lots and lots of things can occur in electronic excited state. So here's an example. If I shine light in of a high enough frequency to go to the excited state to the dissociation limit of a vibration. Remember that this is the potential energy curve for stretching a bond. If I reach the dissociation limit, the molecule can just vibrate back and forth. And if I'm high enough, it just zoom, the molecule falls apart. A much trickier kind of thing is if you have several excited states and one of them is said to be unbound. If you get into this state, maybe you have a bond order of 0, and you can have an internal conversion between these states. And if you wind up in an unbound state where the potential doesn't try to keep you contained at a bond distance, then that can occur. Okay, so enough about those topics. I do want to tell you more about how lasers work. I think most of us find that lasers are pretty neat things. I've been lucky to grow up with lasers. I think I was able in my graduate research to use the first commercial helium neon laser for doing Raman spectroscopy. You can now buy these for something like $500 from Fisher Scientific. Back when I was a student, we had to pay $25,000 in 1960s money for it, and that money's worth like $250,000 now. That's the same laser that's used in supermarket scanners, by the way. So anyway, it's been pretty exciting to see laser developments and how they get better. The old ones that have been around get cheaper, but there's always newer ones that people want to have, and then we still pay a lot of money. The last system that we used is based on neodymium and yttrium aluminum garnet, and that cost us about $250,000 in today's money. But we got a lot of nice results from it, and we thank the National Science Foundation for buying it for us. Okay, to understand lasers, first of all, the word is an acronym. It stands for light amplification by stimulated emission of radiation. So we're going to stimulate molecules to go from their excited states down to ground states, and we'll be able to get extra photons out by this process. The first lasers were actually called masers, and that was microwave amplification by stimulated emission of radiation. And that's because the fellow that discovered it worked at two closely spaced levels in the microwave region of ammonia molecules, actually. But here's the basic principle to understand as such. I mentioned this before, but whether you have absorption or emission depends on relative populations. Most molecules have highly populated ground states, and then you can calculate how many molecules are in an excited state, and it's usually a lot less. I've given you formulas for this already, and I'll derive those for you later when we talk about statistical mechanics. Emission is just as probable, but you're not likely to see it much because there's only a few molecules in the upper state, and so you'll see very little coming down, and will be a lot more of that light being absorbed trying to go up. Now, both of these transitions can be stimulated. As always, delta E is equal to h nu. So absorption we've talked about over and over and over again. We shine in a photon, energy h nu. We have conservation of energy. The molecule or atom gains this much energy. This diagram is a little bit missing. Looks like I whited something out, but then I didn't fix it. If you put a photon coming in to a molecule that has if you put it into a molecule that is in an excited state, it also stimulates a photon to come out. I think I stuck this in your note. Okay, yeah. This is a much better representation of what's going on. Laser was discovered by Charlie Towns. He's come to A&M many times. Many summers, our Institute for Quantum Studies and Engineering has meetings in Wyoming, and Charlie's come there and participated. He lived well into his 90s, but now passed away fairly recently. Anyway, he's the guy that used the microwave on ammonia first. Okay, so here's our picture. We've got to get molecules or atoms into an excited level. So we're looking at one single molecule. We shine in an incident photon, and that photon stimulates, that's why we have the S in laser, stimulates this molecule to drop from the higher state to a lower state. And so to have conservation of energy, we now have two photons coming out. So the first photon doesn't get absorbed, it just tickles this upper system to give off another photon, and we get two photons. So that's how lasers are going to work. One photon will generate two, two will generate four, four will generate eight, eight will quickly generate 16, and so on. But the key to it is we have to have what's called a population inversion. We have to get more molecules or atoms into an upper state than our inner ground state. So we have to be very clever about how we're going to do that. Okay, so I guess ignore this picture and look at the one we just looked at. That should have had one photon in and two coming out right here. Okay, so as I said, there are general principles here. We have to have a population inversion where the excited state has to have more molecules than the lower state. Most often, the lower state will not be a ground state. It will be some other state in the atom or molecule that we go to. And I'll give you examples of that. Secondly, in order for this to work, you have to have something like a laser tube. In this case, this is an example for a helium neon laser or an argon ion laser or a krypton laser. This is a laser that just has a gas flying around in it. That gas may wind up getting ionized or not, but it has very specific quantum levels, very specific energy levels. And so just like that picture that I showed you, we have to get H nu to be just right. And so once one photon is stimulated to give two photons, they start flying around back and forth in this laser tube. And you have to have very precisely designed mirrors. So these mirrors have to be exactly spaced. So you get an even number of waves traveling between these two mirrors. If you don't have exactly an integer number of waves, you're going to have destructive interference and you can't get lazy. In addition, the people that designed this had to be really clever, and not only did they have to have highly reflecting mirrors, but one of the mirrors has to let a little bit of the light out. So about 1% of the laser beam is out. So again, fantastic optical design to make these things work. And so it was mostly in the 1970s that people started building really good argon ion lasers, which are now commonly used for LASIK surgery, or my older daughter is an ear, nose, throat surgeon. She uses them for delicate surgery in the ears and stuff. Anyway, these are easily purchasable for a high price, of course, if they have to be very good. But anyway, the technology of this is quite understood. So point two is you have to design this in a way that you keep enhancing the beam. So more photons generate more and more photons, and they can only do that if they're in phase. And so the company that's best known for making these type of lasers is called Coherent, or initially Coherent Radiation. So this has to be a coherent beam coming out. Now notice we're only getting 1% of the beam out. So if we have a high powered laser that says maybe putting 1 watt out, we've got 100 times more energy within that laser tube taking place. So I won't have time because of shortage of lecture time to tell you about military applications of lasers, but I stuck some stuff into your lecture notes that you can look at. Okay, so some lasers are continuous, that the beam just keeps flying back and forth. Another type, like a carbon dioxide laser, which is a mixture of carbon dioxide and nitrogen, they're pulsed. You get everything set up, and all of a sudden you make the optics right, and boom, you might get whatever, 10,000 watts of energy coming out that can blow apart a concrete wall, for example. Okay, so we're just about out of time, but to give you an idea how this works, and we'll talk more about this then on next Monday. This is a carbon dioxide laser. which is a mixture of nitrogen gas and carbon dioxide. So these are separate molecules in the chamber. We basically use electrical discharge, high voltage, and it excites the nitrogen diatomic molecules into its excited state. Now you remember, we cannot do this optically. We cannot do this with just plain light, because N2 does not have a dipole moment, so you can't get direct absorption of light. So we excite the nitrogen molecule like that, and it can't re-emit very easily, because that would again require a dipole moment. So the chamber is full of CO2 also, and the N2 molecules can combine with the carbon dioxide, and the nitrogen vibrational frequencies, along with the rotational structure, coincide very closely with the antisymmetric stretching frequency of carbon dioxide. And so a collision just converts the nitrogen energy into the vibration of the carbon dioxide. And then the design of the laser system is such that we want to enhance radiation coming back to the symmetric stretch. Notice we don't try to come back to the ground state of carbon dioxide, because there would still be more molecules there. But we haven't excited the symmetric stretch. We've excited some of the antisymmetric stretch. So we have a population inversion. So you have to be really, really clever when you design these systems to make these work. There's a lot of arrows here. And so if you make a CO2 laser, you could pick off individual rotational energy changes. Or if you just want a lot of power, then you let a lot of this radiation come back out. And it would come out at about 950 wave numbers is the energy distance between these two systems. We've run out of time, but I mentioned the power of this laser. I did consulting for Brooks Air Force Base in San Antonio for many years, and it wasn't on CO2 lasers, but one time they had gotten one and they were very proud of it, and they said, "We want to show you our new laser." So they took me into an experimental lab where they put a big block of concrete on the floor there, and then they zapped it with a CO2 laser, and it blew off into about 1,000 pieces. Obviously, we were all shielded from that. But think about that, how amazing this is. We're just looking at the little vibrational energy change in CO2, but if you can focus it all, you can do terrific things. The military tried using the CO2 laser to blow up missiles, but since the beam is in the infrared, if you have a cloud there, water vapor and other stuff absorbing light, then it's very weather dependent. And so I think they've totally given up on trying to use CO2 lasers. Okay, well, enjoy your extended time over the weekend. Color some eggs if you're so inclined. And we will talk again on next Monday. Hopefully we'll have the exam graded sometime this week.